Okay, my name is Brad Dickinson, and this is my fatigue optimization of a simplified wing. The initial problem is that structural failures are usually not due to static loads, but are actually fatigue, and fatigue failures are very difficult to predict. So analysis is time-consuming and expensive, so any effort to include that in design could save a lot of time and money. My initial proposal was just to model a simplified wing with spars and ribs, similar to what's shown, and then optimize it for fatigue. But that's changed when I learned about topology and fatigue optimization at the same time using HyperWorks and OptiStruct. The first step was to build a finite element model. I did both 3D and 2D, as you can see there. The dimensions and loads were inspired by the F-18 Super Hornet. And you can see in those figures that the blue or purple areas, that's my design space. And then the green border is not designed. So the first thing I did was I actually did just topology optimization with static loads. And you can see the result there. My objective was just to minimize the volume of the design space. And the constraint was wingtip displacement. So you can see in the results, there is sort of a spar there in the middle and some ribs, but obviously this would need some refinement, but I had initial results. So I went on to the fatigue optimization where it needed additional inputs. So the first one is just the material stress life curve for aluminum. So on the left there, you can see that from the mill handbook or MMPDS now, that's the stress life data for aluminum. And I use that data to approximate the curve into HyperWorks and OptiStruct. So that's what you can see there on the right. The next step is actually defining the load time histories. So we can see here is I have bending, torque, and shear. Now obviously bending and torque, those loads are what would result in a bending or torque. But the way the spectrum works is you have the loads that are applied in that cycle from peak to valley. And HyperWorks actually provides a process manager for applying these inputs, and it's a step-by-step process, which is where you actually give it the stress life curves for any materials you have and the load time histories. You can see on the bottom that I have my bending time, load time history that corresponds to the bending static load case and so on. And on the right, you can see in the load collectors how many additional cards were created using that step-by-step process behind the scenes. My objective was still to minimize the volume of the design space, but my constraint was actually life, and I wanted the life of the parts to be greater than 1,000 cycles. OptiStruct defines the entire load history as one cycle. So these entire load histories are considered one cycle, even though they're, in fact, they're actually like 500 cycles. So these are ultimately my results. My initial run was performed with the 3D model, and the runtime was over 8 hours. So I couldn't repeat that because I didn't have that much time. So I decided to switch to 2D, and the runtime went down to like 5 minutes, which was much more manageable. The red areas here in the figure are what have the minimum life of 1,000 cycles, which is, you can see, is pretty much the entire wing. But you can see, a semblance of spars and ribs, so it does kind of look like a wing. But a lot of additional work needs to be done. So the future work, those results weren't really convincing to me. I know from experience that the entire wing is not life critical. Obviously, there's going to be stress concentrations like holes. That's usually where fatigue cracks emerge. You would need to refine the loads, constraints. There's more shape refinement for manufacturing. That shape there in the results, that can't be manufactured. And then a better understanding of HyperWorks. There's all kinds of different optimization routines that can be done. And that's pretty much it. So thank you very much.